Mercury. Barely larger than the Moon, Mercury is the smallest planet in the solar system, 20 times less massive than the Earth. It is also the closest to the Sun, since it orbits at only 0.4 astronomical units from our star, i.e., at only 0.4 times the distance from the Earth to the Sun. Although it is very close to the Sun, with an average surface temperature of 356 degrees Fahrenheit, Mercury does not hold the record for highest temperatures. This one belongs to Venus, because of its very dense atmosphere, which creates a powerful greenhouse effect. On the surface of Mercury, which has almost no atmosphere, the light from the Sun is 7 times brighter and more intense than on Earth, and our star would appear 3 times larger in the sky to an observer. Mercury is the fastest planet in the solar system, because at 29 miles per second, it takes only 88 days to go around the Sun. At the end of 2011, as 3/4 of the primary mission time had passed, the Messenger probe had provided new insights into Mercury in several areas. Enigmatic photographs of bright deposits at the bottom of some craters had been taken during Messenger's pre-orbit flybys. New photos, taken with a resolution of up to 10 yards per pixel, revealed that there are groups of cavities at these locations, varying in size from a few hundred meters to several miles. These formations are often surrounded by halos of highly reflective material that are usually associated with rocks ejected from the cratering process. These formations, which are among the newest and brightest on the planet, have never been observed before on any other planet or moon in the solar system. The origins of these depressions is not explained. However, their appearance, which gives the impression of being the result of an etching, suggests that they were formed by removal of material from the surface. One of the theories put forward is that these depressions result from the sublimation of volatile elements contained in the rocks. On the other hand, the pictures taken confirm that the deformations affecting Mercury's crust are essentially linked to the contraction of the planet and are at the origin of gigantic lobed escarpments and faults. But there are also dozens of zones, generally located inside craters or basins, which show, on the contrary, signs of expansion of the crust. The X-ray spectrometer has made several important discoveries about the composition of Mercury's soil. Unlike the Moon's soil, Mercury's soil is not dominated by feldspar-rich rocks. The measurements also confirm telescope observations from Earth, suggesting that sulfides are present on Mercury's surface. As a result, the blocks of material that formed the planet were less oxidized than those used to form the other inner planets. This theory would have important implications for our understanding of volcanism on Mercury. Messenger's altimeter has shown the highest peaks to rise to 5 miles, comparable to Everest on Earth. The onboard magnetometer determined, after several orbits, that Mercury's magnetic equator is 300 miles north of the planet's center. The molten metallic core, located at the heart of the planet, at the origin of the magnetic field, thus has an important north-south asymmetry. As a consequence, the magnetic field has a large hole at the South Pole, which allows solar wind particles to hit the surface of Mercury. This phenomenon pulls atoms from the surface, which feed the tenuous atmosphere of Mercury while polishing the ground. Other results were produced during the extensions of the mission, as the neutron spectrometer of the space probe has definitively demonstrated that water ice was present on the surface of Mercury, despite its very high temperature, up to 752 degrees Fahrenheit. This ice is stored in permanently shaded craters in the polar regions of the planet. The cameras show in these places a dark material which, according to hypotheses of the scientists, would be constituted of a material rich in organic molecules, like comets and asteroids, which are supposed to be at the origin of this water. This discovery calls into question the model of formation of the planet. The metallic core of Mercury, by cooling, has caused a decrease in the diameter of the planet due to the smaller volume occupied by the metal in solid phase. Cliffs, several miles high and several hundred miles long, resulting from this contraction, have formed and crisscrossed the planet's present surface. Data collected by Messenger's altimeter have allowed us to reevaluate the diameter reduction to 4 miles. During its mission, Messenger circled Mercury 4,104 times, taking more than 270,000 pictures. Between November 3rd and 16th of 2010, the wide-angle camera of Messenger took 34 pictures, which allowed to obtain a portrait of the whole solar system by photomontage. Only the planets Uranus and Neptune are not included because, located between 1.5 and 2 billion miles, they cannot be discerned at this distance. After having studied the topography of the northern hemisphere and characterized the volatile elements present in the constantly shaded craters of the poles, the probe crashed on the surface of the planet in April 2015. Now it's time for a new mission, currently on its way to Mercury, Bepi Colombo, which left on October 19, 2018. The probes of this mission of the European and Japanese space agencies will be placed in orbit around the planet in December 2025. Venus. Venus, jewel of the sky, known to ancient astronomers as the morning star and the evening star, considered then, at the time, as two different celestial bodies. The planet Venus owes its name to the Roman goddess of love and beauty, veiled by thick swirling clouds. Astronomers refer to Venus as Earth's sister planet. The two planets are similar in size, mass, density, and volume. They were formed at about the same time and condensed from the same nebula. However, its destiny decided otherwise and made it, over time, very different from the Earth. It has no ocean and is surrounded by a heavy atmosphere composed mainly of carbon dioxide. Its clouds are composed of droplets of sulfuric acid. The atmospheric pressure at its surface is 93 times that of the Earth at sea level. But then, how did it get there? The second closest planet to the Sun has seen little by little its oceans evaporate. Now, water vapor is a formidable greenhouse gas, allowing the Sun's rays to heat the planet without letting the heat escape. Global warming accelerated, and in a few 100 million years, its ocean evaporated completely. The water then concentrated in the highest layers of the atmosphere. Then, the ultraviolet rays of the Sun broke the water molecules. The oxygen atoms fell back to the surface, while the lighter hydrogen atoms were lost in space. Arid, without plate tectonics nor regular volcanism, Venus became unable to evacuate its internal heat, and during hundreds of millions of years, the pressure was in constant increase. When this pressure reached its peak, the planet released carbon dioxide into its atmosphere through volcanoes. This CO2 now replaces water as a greenhouse gas, and the volcanoes, much more numerous on Venus than on Earth, perpetually release it. In this way, carbon dioxide accumulates massively in the atmosphere. Today, it makes up more than 97% of the atmosphere on Venus. The average temperature is 860 degrees Fahrenheit, but can rise to 968 degrees Fahrenheit. The sulfuric acid is another gas entering the composition of the atmosphere of Venus. It is this gas, very reflective, which makes Venus appear so bright in our sky. And sometimes this sulfuric acid falls down in the form of very corrosive rains. Venus turns around the Sun every 225 terrestrial days, but contrary to the other planets of the solar system, Venus has a retrograde rotation, that is to say backwards. Thus, the Sun rises in the west and sets in the east. This rotation is particularly slow, so that from one sunrise to the other, it takes no less than 8 Earth months. Venus thus has days longer than its years. A Venetian day lasts 243 terrestrial days. The atmosphere of Venus is very thick and very dense. On the surface, the atmospheric pressure is 93 times higher than on Earth, and the density is about 50 times higher than our air diameter. While on Earth, the only volcanic complex of this size is the island of Hawaii. Nearly 1,000 impact craters on Venus are evenly distributed on its surface. About 85% of the craters are in perfect condition. The number of craters, as well as their well-preserved condition, indicate that the planet underwent a global resurfacing about 300 to 600 million years ago, followed by a disintegration of volcanism. On Earth, the crust is continuously moving, but Venus would be unable to sustain such a process. Without plate tectonics to dissipate the heat of its mantle, Venus undergoes instead a cyclic process in which the temperatures of the mantle increase until reaching a critical level, which weakens the crust. Then, over a period of about 100 million years, subduction occurs on an enormous scale, completely recycling the planet's crust. These extreme conditions made the exploration of Venus very difficult, and the probes sent to Venus lasted very little time on the surface of the planet before they stopped working. The first pictures came from the Mariner 10 in 1974, which passed by Venus on its way to Mercury and took ultraviolet photographs of the clouds, revealing the extraordinarily high wind speeds in the Venusian atmosphere. In 1975, the Soviet landers Venera 9 and 10 transmitted the first images of the surface of Venus, which were in black and white. In 1982, the first color images of the surface were obtained with the Soviet landers Venera 13 and 14. These images allowed us to discover that the surface of Venus was covered with sediments and relatively angular rocks. The ground shows evidence of extensive volcanism, and sulfur in the atmosphere may indicate recent eruptions. The probe's microphones recorded atmospheric wind noise in an effort to measure wind speed. This was the first sound recording on another planet. Some years later, the surface of Venus was mapped in detail by Magellan in 1990. According to the information collected by the American probe Magellan, the internal structure of Venus would indeed be comparable to the terrestrial structure. It would be composed of a solid inner core, called the seed, and a liquid outer core. This core would be surrounded by a solid and viscous mantle and a solid crust. But this model remains hypothetical, and the question of the composition of the Venusian core remains open because a question persists. If Venus has the same internal structure as the Earth, how do you explain that it does not generate an intrinsic magnetic field? Indeed, the external core of the Earth is made of a hot and electrically conductive liquid, inside which convection movements occur. This conductive layer, combined with the rotational motion, produces a dynamo effect that maintains an electric current system known as a magnetic field. The absence of an internal magnetic field of Venus could be explained in two different ways. Either the rotation of Venus would be too slow to maintain an electric current, or the core of the planet would be solid. Several other missions explored Venus from space in the following decades, but today Akatsuki, the Japanese probe, is the only one currently present around. Earth. The planet with thousands of colors and the cradle of humanity. The oasis of life still has much to teach us about the mystery and origins of our existence. Where to start? There's a lot to tell, but sometimes images speak louder than long speeches. While waiting for a complete video on the subject, the fourth planet farthest from the Sun, small by its size, about half an Earth, but large by its scientific interest, would have once possessed warm, salty seas with freshwater lakes, probably snow on top of its mountains, clouds, and a water cycle. In 2015, the presence of water in brine, a liquid close to the salt water of our oceans and saturated with salts, would even have been detected by the American probe Mars Reconnaissance Orbiter. The salts, which are very absorbent, lower the freezing point of water, allowing it to remain in liquid form and to flow at temperatures below 32 degrees Fahrenheit. Indeed, the surface of the red planet oscillates between 68 and negative 225 degrees Fahrenheit. Even crazier, NASA made the announcement in early June 2018 of the identification by the rover Curiosity of a methane cycle on the red planet and organic molecules. The American rover on Mars since 2012 has made it possible, thanks to the SAM instrument, to identify chains of atoms containing carbon and hydrogen in rocks that are over 3 billion years old. At the time, liquid water would have flowed on Mars. Thus, two ingredients necessary for the appearance of life were probably gathered at the same time on the red planet. Mars is a telluric planet, i.e. rocky, 10 times less massive than the Earth. Seen from the blue planet, it appears reddish due to the iron oxide-rich dust that covers its surface. Once hydrated, the iron oxide becomes rusty, hence the ochre color of our neighboring planet. This is why it has been associated with war since ancient times, hence its name referring to the god of war in Roman mythology. The poles of Mars are permanently covered with whitish caps, which vary greatly depending on the season. At the beginning of the northern spring, for example, the ice of the North Pole exposed to the sun becomes sublime. In other words, it goes directly from a solid state to a gaseous state. This sublimation then creates air masses, which generate winds that raise important quantities of dust and are likely to trigger dust storms on the scale of the whole planet. On the other hand, the planet Mars is characterized by a very clear opposition between the northern hemisphere, made of vast, smooth plains, and the southern hemisphere, made of plateaus rich in impact craters. The northern hemisphere is between 0.6 miles and 2 miles lower than the southern hemisphere, and the thickness of the crust is 20 miles against 35 miles for the southern plateaus. This dichotomy would appear about 4 billion years ago. To explain this phenomenon, there are two theories. One is related to the internal dynamics of the planet at the level of the mantle and plate tectonics, and the other one to one or more large bombardments that would have led to the melting of the terrain of the northern hemisphere. It should also be noted that the terrains of the northern hemisphere are younger than those of the southern hemisphere, as well as marked by the former presence of abundant and acidic liquid water. At the contact of the geological limit materializing the dichotomy, these regions gather a strong concentration of volcanoes. It is on the bulge of Tharsis that the largest volcano of the solar system is located, Olympus Mons, which culminates at more than 21,000 yards of altitude. Moreover, unlike Earth, Mars does not have plate tectonics. hence the colossal size of its volcanoes. On our planet, the crust moves relative to the hotspot in the mantle, which ejects lava onto the surface, forming a succession of small volcanoes. On Mars, the lava accumulates in a single point, giving rise to gigantic volcanoes. Today, the red planet has lost almost all of its internal geological activity. Only a few landslides, CO2 geysers at the poles, earthquakes, and small lava flows still occur. On the other hand, the southern hemisphere of Mars is dotted with impact craters. Argyre Planitia and Hellas Planitia are the two most remarkable. The second one, of about 1,370 miles in diameter and 9,500 meters deep, is the largest observable impact structure on the planet. Unlike lunar craters, whose appearance does not change with time, Martian craters are subject to erosion of atmospheric origin, which alters their shape, rounds their edges, and covers their interior with a thick layer of dust. However, they remain clearly visible. In addition, the surface of the red planet has the largest canyon in the solar system. The gorges of Valles Marineris are up to 8,000 meters deep and extend from the west to east for more than 1,800 miles. In the vicinity of Valles Marineris, a multitude of small valleys evoke dry riverbeds. This is a clue that points to a history of Mars, during which liquid water flowed freely. Finally, the surface gravity on Mars is only 38% that of Earth. Microgravity is known to cause health problems such as muscle loss and demineralization, but this is not to discourage plans to colonize the red planet. The InSight mission's seismometer that arrived at its destination on November 26, 2018, has shed some light on a certain point. Martian earthquakes are weaker but more frequent than predicted by theoretical models. In 13 months, the seismograph recorded nearly 460 events, mostly micro-earthquakes. By analyzing the seismic waves from a handful of earthquakes, the most intense observed over 2 years, scientists were able to refine our knowledge of the internal structure of Mars. The seismic recordings allowed to distinguish 3 layers in the subsurface: the duricrust, an indurated layer of a few inches; the regolith, a superficial stratum formed by materials crushed by impacts during billions of years; a weathered layer about 10 miles thick. Underneath is a consolidated deep crust, where the scattering and attenuation of the waves are similar to those of the terrestrial crystalline massifs. The magnetometer detected a magnetic field 10 times higher than expected. The rocks near the landing site are too young to have been magnetized by the ancient global field of Mars, so the measured field must come from deeper rocks. InSight also detected magnetic pulses in the middle of the night, whose origin is still unknown. The Martian atmosphere is composed of 96% carbon dioxide, 2% argon, 1.9% nitrogen. Images taken from the surface of the planet show that the sky appears orange, which is probably due to fine particles of iron oxide dust, the same as on the ground, in suspension. The atmosphere of Mars is very thin, with a pressure of less than 1% of the Earth's value. And where is Perseverance in all this? Well, 8 months after landing on the red planet, the Perseverance rover has delivered its first results. As scientists expected, the Jezero crater in which the robot landed is indeed a lake that has been dry for about 3.6 billion years. According to the very first study conducted by data collected by the French Perseverance Supercam, the lake extended over a diameter of about 17 miles and was several yards deep. Finally, the red planet has no rings, but two small natural satellites, Phobos and Deimos. It is the closest to its planet, orbiting at about 5,500 miles from Mars. It falls towards Mars at a rate of 18 centimeters each year because of the gravitational attraction of the planet. At this rate, in 11 million years, Phobos will be so close to the Martian surface that the gravitational pull will make it disintegrate at about 2,500 miles altitude. Deimos, on the other hand, is smaller and more distant. It orbits at an altitude of about 14,000 miles. Like its counterpart, it is irregularly shaped and dotted with craters. According to the latest scientific publications, these two moons, named after the twins of the gods Mars and Venus in Roman mythology, would be the residue of an impact between the red planet and an asteroid. The debris of this collision would have formed a ring in which a dozen satellites would have been accreted. Only the two most distant would have survived, Phobos and Deimos. Between the orbits of Mars and Jupiter lies the main asteroid belt of the solar system. In this region, it is estimated that there are over 150 million objects. The largest of these is the dwarf planet Ceres. Dawn is a NASA space probe whose mission is to study Vesta and Ceres, the two main bodies in the asteroid belt. Launched in 2007, Dawn began its observations in 2011, orbiting Vesta and then Ceres, and completed them in 2018. But what did the probe see on Ceres? The images provided by Dawn's camera show numerous craters scattered across a globally homogeneous surface with bright spots. These are deposits of carbonates and other salts. This surface proved to be relatively complex, with the superposition of young and old terrains. Numerous clues, such as the amount of hydrogen measured, direct identification, and the trace of flows, demonstrate that ice is abundant at high latitudes. But the presence of large craters up to 150 miles in diameter argues for a crust more solid than ice. Measurements of the gravitational field and the study of surface formations indicate that the internal density of Ceres increases as one approaches the center of the dwarf planet. This indicates that Ceres is a differentiated planet with a dense core composed mainly of rocks and a mantle rich in water. This characteristic distinguishes Ceres from other asteroids. Ammonia has been detected on the surface of Ceres. This discovery suggests that the materials composing Ceres were formed in the outer part of the solar system, and confirms the hypothesis that it has undergone one or more important changes before adopting its current configuration. Dawn's infrared spectrometer has identified the origin of the bright spots visible in the Iapetus crater region. They are constituted by an accumulation of carbonate. The amount of this mineral present at the site exceeds anything found in similar formations on Earth. Iapetus is a recent crater on a geological scale, with an estimated age of 80 million years. The presence of carbonates on Earth points to the existence of hydrothermal phenomena, which implies the presence of hot water. The carbonate on Ceres suggests that the interior of the asteroid is much hotter than previously estimated by scientists. Scientists are now certain that liquid water was present beneath the surface in the recent geologic past. The visible salts are remnants of an ocean or pockets of water that reached the surface. Dawn's infrared spectrometer also indicates the presence of ammonia-containing salts in the Iapetus crater. Ammonia-containing clays have been detected previously at other locations on the surface of Ceres. This discovery, together with that of the carbonates, supports the thesis that Ceres formed in the outer part of the solar system towards the orbit of Neptune, and that its orbit then moved towards the inner part of the solar system. However, the study of the surface of Ceres seems to contradict this hypothesis. Indeed, craters deeper than 1 mile, which were formed by an impact several billion years ago, do not show signs of deformation. If the surface was composed only of ice, this kind of relief should have faded over the periods of heating and cooling. According to the study carried out, the external layer of the surface would not contain more than 30 to 40% of ice, the remainder being constituted of rocks and minerals. This rocky constitution of the surface is common among bodies formed near the Sun, and thus contradicts the conclusions drawn from the presence of minerals. Dawn's instruments took about 31,000 photos of the surface during its year-long orbit around Vesta. This data allowed us to determine that Vesta is very different from other asteroids. Its geology is complex. It is a differentiated body with a dense core of nickel and iron, whose diameter would be between 130 and 140 miles, knowing that the diameter of Vesta is 330 miles with a mantle and a crust above the core. Vesta has characteristics very close to those of a planet. This affiliation is supported by the discovery of terrestrial meteorites from Vesta, presenting evidence that a strong magnetic field existed 3.6 billion years ago. There was therefore, at the time, a liquid metallic core capable of generating it. Traces of this magnetic field could remain today. The two hemispheres present a very different aspect. The northern hemisphere of Vesta is riddled with impact craters, which trace a turbulent 4.5 billion year stay in the asteroid belt. The southern hemisphere was completely reshaped by a huge impact, which occurred at least 2 billion years ago, and by a second, even larger collision that occurred about 1 billion years ago. These two events created the basins of Venonea, 250 miles in diameter, and Rhea Silvia, 310 miles in diameter. In the center of the largest of these basins stands a peak twice as high as Everest. The impact was so large that it almost burst Vesta, and it left an extensive network of huge depressions near the equator, hundreds of miles long and 9 miles wide. These impacts caused the expulsion of a large quantity of rocks in space, some of which have since fallen to Earth. Vesta has the particularity of being a particularly bright object, the only asteroid of the belt visible to the naked eye by an observer located on Earth. This is due, according to the observations made by Dawn, to the presence of areas of variable size, from 100 yards to 10 miles in diameter, which are twice as bright as the rest of the surface of Vesta, and which are mainly found in or near the impact craters. These terrains are made of the original asteroid material, dating back 4 billion years, exposed by the impact of asteroids that crashed into Vesta's floor. Alongside these bright surfaces are dark areas that could correspond to remnants of asteroids that crashed at low speed onto the surface, or portions of the basaltic crust that melted as a result of more violent impacts. The instruments of the space probe have allowed us to determine the composition of the rocks on the surface, mainly made of minerals rich in iron and magnesium. Landslides, impact craters, as well as very fine measurements of gravity variations allowed us to identify the composition of the surface strata. A surface temperature map was established. It shows that the temperature can vary from -10 degrees Fahrenheit in the places with the best exposure to the sun to -148 degrees Fahrenheit in the shaded areas. Although the asteroid is composed of half ice, it is not visible on the surface according to the observations. Indeed, the axis of the asteroid is strongly inclined at 27 degrees, that is to say, an angle higher than that of the Earth at 24 degrees, which consequently results in all points of the surface, including the sides of the crater, being exposed to the Sun at one time or another during the year. Jupiter is impressive because of its size and the storms that constantly rage on its surface. The gas giant has been observed by astronomers since antiquity, yet many unknowns remain about its nature and those of its moons. Mysteries that the American mission Juno begins to elucidate, soon completed by the European JUICE. Jupiter is a gas giant planet, mostly composed of gas at 95%, including helium and hydrogen, which are light gases. It is, however, more massive than all the planets of the solar system combined. Its volume is equivalent to 1,321 times that of the Earth. Named after the Roman god Jupiter, or Zeus in Greek mythology, it is the fifth farthest from the Sun. Although Jupiter has been known since antiquity, there is still much uncertainty about its structure and composition. According to current knowledge, the star is made up of a thin gaseous atmosphere 600 miles thick, rich in molecular hydrogen at 86% and helium molecules at 13%. There are dense clouds with brown, red, and white tints due to the presence of ammonia. Then, the temperature and the thick pressure increasing with the depth, the hydrogen would condense progressively in the form of a thicker and thicker fog, being transformed finally into a sea of liquid molecular hydrogen, poor in helium, located between the low part of the gaseous atmosphere and approximately 6,200 miles of depth. Between 6,200 miles and 37,000 miles, where the temperature exceeds 36,000 degrees Fahrenheit and the pressure reaches 40 million Earth atmospheres, one would then find liquid metallic hydrogen, a bit like Mercury. Indeed, the very strong pressure breaks the hydrogen molecules, making them lose one or more electrons, and thus transforming them into charged chemical species, ions. It is this layer that would be at the origin of the magnetic field of Jupiter, the most powerful of the 8 planets of the solar system. Finally, at the center of the planet, ongoing research points to the existence of a solid core of rock or ice, with a mass equivalent to about 3 times that of Earth. Jupiter is a complex and turbulent world. Data collected by instruments on the Juno spacecraft challenge many scientific assumptions about the processes at work. Juno has identified a new radiation belt at the equator just above the atmosphere, indicated by a bluish spot. The spacecraft also crosses an already known radiation belt located at high latitudes. On the other hand, a new belt of radiations was discovered at the level of the equator immediately above the atmosphere. The images provided by the Juno camera show that the regions of the 2 poles are occupied by storms the size of the Earth, very close to each other. Scientists wonder about their mode of formation and their dynamics. Are they permanent phenomena? Does their configuration evolve over time? Do the storms move? The data collected on the polar auroras show that the processes at work are different from those on Earth. Electrons accelerated at the poles have energies reaching 400 kiloelectron volts, i.e. 10 to 30 times that of the Earth. But to the surprise of scientists, despite this enormous electrical potential, the polar auroras are not permanent, and the source of the most intense polar auroras is not related to this characteristic. Juno's camera took very detailed pictures of Jupiter's surface. In particular, one of Jupiter's most iconic features, the Great Red Spot. According to radiometer data, the Great Red Spot extends at least 150 miles deep and is hotter at its base than at its surface. It corresponds in reality to a giant storm comparable to a hurricane. Juno flew over this eye of Jupiter at an altitude of about 5,500 miles. In other words, very close. It determined that the cyclone measured about 10,000 miles, or 1.3 times the diameter of the Earth. However, the main information for which scientists still had no estimate concerns the depth of the storm. Thus, the eye of Jupiter would be 50 to 100 times deeper than the Earth's oceans, and hotter at its base than at the top. Its winds, which can reach 400 miles an hour, are due to this temperature difference. The onboard radiometer indicates that the deep layers of Jupiter's atmosphere, 25 to 50 miles below the cloud tops, are restless, contrary to the general consensus of scientists that there is no incident energy at this depth. Moreover, based on gravity field measurements, the radiometer does not allow the probe to measure beyond a few hundred miles. The Juno science team discovered that the winds and the horizontal stripes visible on the surface extended to a depth of 1,800 miles, thus setting a lower limit of the atmosphere at a much greater depth than expected. Contrary to the hypothesis, this atmosphere is not made up of nested layers characterized by differentiated rotation speeds. Below this atmosphere, the lower layers, whether liquid or solid, have a single rotational motion and behave as if they were a single entity. Considering the results obtained by measuring the gravity field, it is possible that the rocky and metallic core of the size of an Earth or a super-Earth existing at the time of the formation of Jupiter has dissolved and mixed with the mantle made of liquid metallic hydrogen. The intensity of the magnetic field of Jupiter, which could be measured with precision, reaches 7.7 Gauss, a higher value than expected. The instrument used was able to demonstrate that it was irregular, which seems to indicate that the dynamo that generates the magnetism is closer to the surface of the planet than expected and would be located above the metallic hydrogen layer. With a launch planned in June 2022, the European Space Agency mission, JUICE, will join Juno in the Jovian environment in 2029. It will observe Jupiter, and especially its three largest satellites, which are Europa, Ganymede, and Callisto, which would each contain an ocean under a solid crust. In the Jupiter system, there are 67 confirmed moons of various sizes, shapes, and compositions. In honor of Jupiter's namesake, they are sometimes collectively called the Jovians. Of these, the four largest, Io, Europa, Ganymede, and Callisto, are known as the Galileans. These four moons are among the largest in the solar system, Ganymede being the largest of all, even larger than the planet Mercury. In addition, three of these moons, Europa, Ganymede, and Callisto, are all believed or known to have internal oceans at or near their core mantle boundary. The presence of warm water oceans is considered an indication of potential life on these moons. Launched on October 18, 1989, the Galileo probe reached Jupiter and its moons 6 years later to study them until 2003. Setbacks and firsts punctuated one of the most exceptional planetary exploration missions. Galileo collects a lot of scientific information, despite the unavailability of its large antenna, which could not be deployed, strongly limiting the volume of data transmitted. Io, with a radius of 1,100 miles and an average distance of 260,000 miles from Jupiter, Io is completely enveloped by Jupiter's powerful magnetic field. The moon has the shortest orbital period of any Galilean, taking about 42.5 hours to complete a single orbit around the gas giant. Io has the highest density of any moon in the solar system and is significantly denser than the other Galilean moons. composed primarily of silicate rocks and iron, its bulk composition is closer to the terrestrial planets than to the other satellites of the outer solar system, which are composed primarily of a mixture of water ice and silicates. Unlike its Jovian cousins, Io has no warm water ocean beneath its surface. In fact, based on magnetic measurements and heat flow observations, it is believed that an ocean of magma exists about 30 miles below the surface. This heat is also responsible for Io's volcanic activity and its observed heat flow. Galileo has flown by Jupiter's satellite Io 7 times, but the first and last flybys produced little scientific data. The observations made have identified more than 100 active volcanoes on the surface of this moon, including Loki, the most powerful volcano in the solar system. These produce lava with an enormous flow, making this moon, according to specialists, a perfect representation of hell. We must go back 2 billion years in the history of the Earth to find phenomena of such violence. The camera of the space probe was able to make close-ups of an eruption of lava rising to more than 1 mile above the surface of the moon. The surface is constantly covered with smooth plains dotted with high mountains, pits of various shapes and sizes, and volcanic lava flows. Its colorful appearance is also indicative of volcanic activity that has covered the surface with sulfuric and silicate compounds and led to the renewal of the surface. Io has the smallest amount of water of all known bodies in the solar system, which is probably due to the fact that Jupiter is sufficiently hot at the beginning of the evolution of the solar system to drive volatile matter like water from its surface. The geological phenomenon are essentially caused by the tidal forces generated by Jupiter, which fluctuate according to the position of Io in its orbit, because the latter is not circular. These forces deform the planet like a rubber ball. The resulting internal friction of the rocks creates enormous amounts of internal heat, which represents a heat flow twice as important as that at the origin of Earth's volcanism. Mountains culminating at 8 miles of altitude were discovered by the space probe. They do not seem to be of volcanic origin. Other photos indicate that these peaks are gradually disappearing as a result of huge landslides caused by their mass. The discovery by Galileo of a hole at the level of Io in the magnetic field created by Jupiter, supplemented by measurements of the gravitational field of the moon, make it possible to deduce that this one has a metal core made up of iron and iron sulfide of a diameter of 500 miles, that is to say, 50% of its total diameter. By carrying out its first overflight of Io at the arrival in the Jovian system, the instruments of the space probe noted the presence of the ionosphere at an altitude of 500 miles, whereas, according to the data collected by preceding space probes, this one should have culminated from 25 to 50 miles. These differences reflect the great variability of this region of space around Io. Europa. If Io could be characterized as a hellish place spewing lava, then Europa would be calm, icy, and watery by comparison. With an average radius of about 1,000 miles and a mass of 8 times 10 to the 22nd pounds, Europa is also slightly smaller than Earth's moon. Its orbit is nearly circular and lies at an average distance of 416,000 miles from Jupiter. The moon takes 3.5 Earth days to complete a single orbit around Jupiter. Galileo has made 9 close flybys of Jupiter's satellite Europa. 2 of these flybys yielded little data after the spacecraft switched to survival mode at a critical time. And the last flyby was done in a context of reduced budget, which allowed only limited observations. Unlike Ganymede and Callisto, Europa has a few craters on its surface, which indicates that a geological process has made them disappear. According to estimates made from observations of other moons of Jupiter, there's an average impact creating a crater of 10 miles in diameter every million years. However, The observations made by the space probe have only allowed the discovery of about 10 craters of this size. The surface of Europa would have, according to the majority of scientists, less than 10 million years of existence, which is younger than anything that can be observed on another planet except the Earth. The images taken by Galileo confirm this theory. They show blocks of crust resembling icebergs floating on an invisible ocean. These blocks are tilted or seem to have rotated on the spot, as if pressure had released them and made them rotate. The surface is also marked by long ridges and fractures surrounded by bands of dark-colored rock and ice. The process at work is probably the result of tidal forces generated by Jupiter and the other moons that lift the surface several tens of yards each day, breaking the ice crust and causing volcanic eruptions of ice and geysers that disperse material from the deep layers to the surface. Europa is clearly denser than the other Galilean moons, except for Io, which indicates that its interior is differentiated between a rocky interior composed of silicate rock and a possible iron core. Above this rocky interior is a layer of water ice whose thickness is estimated at about around 60 miles. Many data converges to indicate the presence of an ocean under the ice layer covering Europa. The youthfulness of the surface, the presence in some region of ice blocks with the appearance of icebergs, can be explained only if the surface ice layer is heated from below by either hot ice or by water in the liquid state. The NIMS infrared instrument found concentrations of salt, sulfates, and carbonates in the youngest regions. Such deposits could be explained by the presence of a salty ocean located under the ice crust. If the waters of this ocean are carbonaceous, enough pressure can be generated to expel the debris observed on the surface of Europa. Moreover, a laboratory experiment reconstituting the conditions prevailing on Europa allowed us to verify that the electromagnetic spectrum of salts is in conformity with this theory. The strongest argument in favor of the presence of an underground ocean concerns the characteristics of the magnetic field of the planet. The magnetometer of the space probe has detected a local magnetic field that seems to be induced by that of Jupiter and not created by the moon. This field would be created by electric currents circulating in the salty and therefore conductive underground ocean. The measurement of the gravity field indicates the presence of superficial layers of low density made up of water in the liquid state or in the form of ice. The presence of liquid water in such a cold region would result from the thermal energy generated by the tidal forces exerted on the moon. The theory of a subterranean ocean gave rise to many speculations on the presence of living organisms on Europa. The observations of Galileo on the magnetic field of Jupiter showed that it exerts on the ions present in the oceans of Europa an influence important enough to cause an oceanic current. This current would have a speed of a few inches per second and a direction opposite to that of the rotation of Europa. This phenomenon could be responsible for the faults observed on the surface of the satellite. Given the combination of these factors, it is considered a strong possibility that organic life also exists in this ocean. Ganymede. The moon of Ganymede is the third most distant moon of Jupiter and orbits at an average distance of 600,000 miles. At this distance, it takes 7 days and 3 hours to complete a single revolution. Like most known moons, Ganymede is tidally locked, with one side always facing the planet. With an average radius of 1,634 miles, equivalent to 0.4 Earths, Ganymede is the largest moon in the solar system, even larger than the planet Mercury. However, with a mass of 3 × 10 to the 23rd pounds, it is half as massive, which is due to its composition, which consists of water ice and silicate rock. Galileo flew 6 times at low altitude, between 160 and 2,000 miles, above the satellite of Jupiter, Ganymede, collecting a lot of data each time. Data on the magnetic field surrounding Jupiter suggests that Ganymede Jupiter's largest satellite, has a magnetic field created by an internal dynamo similar to that of the Earth, i.e. a metallic core. Depending on its nature, whether it's pure iron or iron sulfide, it could be located 250 or 800 miles from the surface and represent between 1.4% and 1/3 of the mass of the Moon. This is the first time that a magnetic field has been discovered on a natural satellite. The surface of Ganymede is constituted by two types of ground. The soil is 40% dark and covered with craters. These grounds would go back to the formation of the Moon. The rest of the surface is composed of light-colored and softer soils called sulcus, which would have been formed more recently following the emergence of underground waters. Ridges sometimes reaching up to 700 miles and several thousand miles long crisscross this type of terrain. These younger terrains could have been formed at a time when the orbit of the Moon was more elliptical, leading to variations in tidal forces that could fracture the ice sheet and generate groundwater eruptions. The craters of Ganymede, with a diameter between 30 and 250 miles, are almost flat, which could be explained by the fact that the ice in which they were dug is a softer material than the rock, in which formed, for example, the lunar craters. In addition to its own magnetic field, Ganymede has a magnetic field induced by that of Jupiter. This one would be, according to one of the scientists in charge of the mission, generated by materials more conductive than ice. The presence of a salty ocean, with the depth of the terrestrial oceans and located 100 miles under the ice layer of the surface, could be at the origin of this magnetic field. Callisto. Callisto is the most distant of the Galileans, orbiting Jupiter at an average distance of 1 million miles. With an average radius of 1,500 miles, or 0.3 Earths, and a mass representing 1% of that of the Earth, Callisto is the second largest moon of Jupiter. It is comparable in size to Mercury, but due to its mixed composition, it has less than 1/3 of the mass of Mercury. Galileo has flown by Jupiter's satellite Callisto 9 times. The data collected indicates that the moon is made of a mixture of iron and iron sulfate rich rocks at 60% and ice at 40%, and that, unlike Ganymede, it does not have a central core identifiable as such. Indeed, located at a greater distance from Jupiter than the other Galilean moons, Callisto was not exposed to as much intense heat resulting from the tidal forces of the giant planet. The process of differentiation, which should lead to a layered structure of greater density with depth and a metallic core, is unfinished. Like Europa and Ganymede, the possible existence of a subsurface ocean on Callisto has led many scientists to speculate about the possibility of life. This is especially likely if the inner ocean is composed of salt water, as halophiles, which thrive in high concentrations of salt, could live there. But the environmental conditions necessary for life to arise, which include the presence of sufficient heat due to tidal bending, are more likely on Europa and Ganymede. The main difference is the lack of contact between the rocky material and the interior ocean on Callisto. While Callisto has the prebiotic chemistry necessary to host life, it lacks the necessary energy. Jupiter's 4 inner moons, Metis, Amalthea, Thebe, and Adrastae, circulate between the 4 Galilean moons and Jupiter. These small satellites, the largest is 170 miles long, could be observed relatively closely when the Galileo mission was extended. Relatively detailed pictures were taken by the spacecraft. Galileo also photographed the collision of comet Shoemaker-Levy 9 with the planet Jupiter. Even today, the study of Jupiter and its moons remains a priority objective. In February 2007, the New Horizons spacecraft on its way to Pluto flew over Jupiter and its moons. Its cameras, more powerful than those of the Galileo, allowed them to take better pictures of the planet and its moons. The Juno spacecraft, launched in 2011, entered a polar orbit around Jupiter in 2016 to study the composition of the atmosphere and the characteristics of the magnetosphere of Jupiter. JUICE, the space probe of the European Space Agency, is to be launched in 2022 and study Ganymede after placing itself in orbit around this moon in 2030. Saturn. The long stay of Cassini near Saturn allowed us to study the structure, very singular, of the atmosphere of Saturn at the North Pole, discovered in 1981 by the space probe Voyager 2. The cloud system has a hexagonal shape, stable in time, with each side measuring 8,500 miles and making a complete turn in 10 hours and 39 minutes. At the center of this formation is the central eye of a hurricane of 1,200 miles in diameter, which drags the clouds in a counterclockwise direction at a speed greater than 310 miles an hour. Saturn also has other vortexes located inside the smaller hexagon. The precise mechanism at the origin of this formation is still unknown. The year on Saturn lasts a little more than 29 Earth years and is divided into seasons, because the axis of the planet is tilted like that of the Earth. A seasonal storm every 29 years, linked to the warming of the surface, has been observed several times before the arrival of Cassini. Called the Great White Spot because of its visible characteristics, it begins with a series of white spots, which gradually extend in longitude until they circle the planet. It is systematically located in the northern hemisphere without being able to explain why. The storm could be studied in detail when it appeared in December 2010, 10 years before the expected date. The space probe determined that the storm is bringing up water vapor and other materials located as deep as 100 miles. The instruments of the space probe observed for the first time, notably within this storm, lightning on both the illuminated and the dark side of the planet. The determination of the sidereal rotation period of the planet is essential to study all the associated physical phenomena, especially to establish the longitude system of a planet. In the case of the telluric planets, it is enough to observe the ground to obtain this rotation period. In the case of gaseous planets, there is no ground, and the core is buried very deeply under the atmosphere of the planet. The only observable period that is related to the rotation of the core of these planets is that of their magnetic field. We therefore study the modulations induced by the rotation of the magnetic field of the planet, studied on its natural radio emissions to know its sidereal rotation period. The rotation period of Saturn was first determined in thanks to the data of the Voyager probe. The sidereal period of Saturn is 10 hours and 39 minutes. In 2000, scientists using radio data from the Ulysses probe observed that the modulation period of Saturn's radio emissions has changed since the Voyager measurements. The new measurements give a period 1% longer than that measured by Voyager. The radio measurements obtained with Cassini confirm the variation of the period. Observations made between 2004 and 2005 around Saturn seem to show that the radio period varies slowly on a yearly scale by a few percent. As the sidereal rotation speed of Saturn's core cannot vary, it is the interpretation of the modulations of the radio emissions that should be properly reviewed. They're mainly emitted on the day side of Saturn's magnetosphere, and they are strongly correlated with the solar wind pressure. Currently, there are different interpretations. The first is a seasonal effect. The height of the sun on the plane of the rings changes the quantity of free electrons on the magnetic field lines, and thus changes the conditions of emission of radio waves. The second is perhaps an effect of the solar cycle. The properties of the interplanetary medium and the solar wind vary strongly with the solar activity. It has been shown that Saturn's auroral radio emissions are very strongly correlated with the fluctuations of the solar wind parameters. The last interpretation is possibly a convection system of Saturn's core, a hypothesis inspired by what happens in the Sun, but rather unlikely. The problem is particularly thorny, because if the rotation period of Saturn is indeed 1% slower than the period measured by Voyager, the whole atmospheric system of Saturn is then in superrotation, i.e., it would rotate faster than the core of the planet, which is difficult to explain. Before the conclusion of the Cassini mission, two scenarios were evoked concerning the origin of Saturn's rings. According to the first scenario, the rings would be the result of a cataclysmic event, such as the destruction of a moon or a comet disintegrated by the gravitational forces acting inside the Roche boundary. They would be, as such, relatively young. In the second case, the rings would be the relics of the formation of the giant planet, and would thus be 4.5 billion years old. The last orbits of Cassini at the end of 2017, which took place between the rings and the upper layer of Saturn's atmosphere, allowed us to decide. By maneuvering at a very short distance from the rings, Cassini was able to make gravitational measurements, observing the influence of the rings on its trajectory, and thus determine the mass of material accumulated. The rings are made of about 15.4 times 10 to the 15 tons of material, which is 20 times less than estimated until now. To give you an order of magnitude, our moon weighs 7.6 times 10 to the 19th tons. With more specific information, Cassini was able to assert that the rings were formed 10 to 100 million years ago, and that they will probably have completely disappeared within the next 100 million years. Originally, the rings must have been much larger and much brighter. The measurements made do not allow to determine precisely the cataclysmic event at the origin of the rings, but traces of it are perhaps preserved in the geological layers of Saturn's moons. The characteristics of Saturn's magnetosphere were poorly known before the arrival of Cassini. The mission discovered that, unlike other planets in the solar system with magnetic fields, Saturn's magnetic field has an axis that coincides exactly with the rotation axis. Cassini determined that the planet's magnetic field undergoes a significant fluctuation, which is repeated with a periodicity of 10 hours and 47 minutes. The scientific instruments of the probe have allowed us to discover that the material present in the magnetosphere has a main origin geyser located at the south pole of the moon Enceladus. The composition of these materials is dominated by ions and molecules produced by the combination of water components ejected by the geysers. Contrary to scientists' assumptions, no significant amounts of the nitrogen that should escape from Titan's atmosphere are found. The end of Cassini involved a series of close passes of Saturn, approaching the interior of the rings, then an entry into the atmosphere of Saturn on September 15, 2017, to destroy the spacecraft. After 22 more orbits, the mission ended with a dive into Saturn's atmosphere on September 15th. The signal was lost only 30 seconds later than expected. It is estimated that the spacecraft burned up about 45 seconds after the last transmission. Around the distant gas giant Saturn is a system of rings and moons of unparalleled beauty. All in all, the Saturn system is just behind Jupiter in terms of number of satellites, with 62 confirmed moons. Of these, the larger moons are divided into two groups: the large inner moons, those orbiting close to Saturn in its tenuous E-ring, and the large outer moons, those beyond the E-ring. They are, in order of distance from Saturn, Mimas, Enceladus, Tethys, Dione, Rhea, Titan, and Iapetus. Mimas. With a diameter of 250 miles and a mass of 1 times 10 to the 20th pounds, Mimas is the smallest and least massive of these moons. It is ovoid in shape and orbits Saturn at a distance of about 115,000 miles, with an orbital period of 0.9 days. The low density of Mimas, estimated to be just slightly greater than that of water, indicates that it is composed mainly of water ice, with only a small amount of rock. Enceladus. Enceladus, meanwhile, has a diameter of 300 miles, a mass of 2 times 10 to the 20th pounds, and is spherical in shape. It orbits Saturn at a distance of about 238,000 miles, and it takes 1.4 days to complete a single orbit. Although it is one of the smallest spherical moons, it is the only Cronian moon that is geologically active, and one of the smallest known bodies in the solar system where this is the case. This is reflected in features such as the famous tiger stripes. Since 2005, several successive observations make Enceladus the most interesting object in the Saturn system, along with Titan. The measurement of the magnetic field of Saturn near the moon highlights that it is distorted by the presence of an atmosphere. Close flybys show that geysers, gushing permanently from the South Pole region, eject at a speed of 400 yards per second, a mixture of water ice and simple chemical compounds. The composition of the plumes also indicates that the subsurface ocean is salty and contains organic and volatile molecules. Photos of the surface of the South Pole, taken from a very short distance, showed a particularly young surface, littered with blocks of ice the size of a house, crisscrossed by fractures suggesting tectonic activity, and topped by a cloud of water vapor. Some deep crevices, called tiger stripes, are the points of emergence of geysers. Successive flybys have confirmed that the surface of the South Pole of Enceladus was undergoing tectonic movements. The engine of this activity could be the tidal force produced by Saturn. This force acts not only on the surface ice layer, but also on the rocky core, as shown by the presence of silica. But the presence of this ocean of liquid saltwater, organic molecules, and volatile substances also indicates that the interior of Enceladus is experiencing hydrothermal activity. This energy source, combined with organic molecules, nutrients, and prebiotic conditions for life, means that it is possible that Enceladus harbors extraterrestrial life. Tethys. With a diameter of 620 miles, Tethys is the second largest inner moon of Saturn. The majority of its surface is made up of a strongly cratered terrain. With an average density of 0.9 grams per cubic inch, Tethys would be composed almost entirely of water ice. It is currently unknown whether Tethys is differentiated into a rocky core and an ice mantle. Dione. With a diameter of 700 miles and a mass of 22 times 10 to the 20th pounds, Dione is the fourth largest moon of Saturn. Most of Dione's surface is ancient, heavily cratered terrain, with craters measuring up to 150 miles in diameter. With an orbital distance of about 230,000 miles from Saturn, the moon takes 2.7 days to complete a single rotation. Dione is composed mainly of water ice, with a small remnant probably consisting of a core of silicate rock. Dione also has a very thin atmosphere of oxygen ions, which was first detected by the Cassini spacecraft in 2010. Although the source of this atmosphere is currently unknown, it is thought to be the product of radiolysis, where charged particles from Saturn's radiation belt interact with water ice on the surface to create hydrogen and oxygen, similar to what happens on Europa. Rhea. Measuring 1,000 miles in diameter and 40 times 10 to the 20th pounds in mass, Rhea is the second largest moon of Saturn. With an orbital radius of about 327,000 miles, it is the fifth farthest of the larger moons and takes 4.5 days to complete an orbit. Like the other Cronian satellites, Rhea has a heavily cratered surface. Rhea is estimated to be 75% water ice and 25% silicate rock. This low density means that although Rhea is the 9th largest moon in the solar system, it is also the 10th most massive. Regarding its interior, Rhea was originally suspected to be differentiated between a rocky core and an icy mantle, but more recent measurements suggest that Rhea is only partially differentiated, or has a homogeneous interior, probably composed of both silicate rock and ice. similar to Jupiter's moon, Callisto. Models of Rhea's interior also suggest that there may be an internal liquid water ocean, similar to Enceladus and Titan. This liquid water ocean, if it existed, would likely be located at the boundary between the core and mantle and would be fed by heating caused by the decay of radioactive elements in its core. Titan. Titan is the largest of the Cronian moons. Indeed, with 3,000 miles in diameter and 3 times 10 to the 20th pounds in mass, Titan is the largest moon of Saturn and accounts for more than 96% of the mass in orbit around Saturn. Titan's composition is half water ice and half rocky material. It is also the only large moon to have its own atmosphere, which is cold, dense, and rich in nitrogen. Another thing Titan has in common with Earth, unlike all other moons and planets in the solar system, is atmospheric pressure. On the surface of Titan, the atmospheric pressure is estimated to be 1.4 times that of the Earth. After a journey of nearly 7 years and 2.1 billion miles across the solar system on the back of Cassini, Huygens landed on Titan. Thanks to its heat shields and the correct deployment of its 2 parachutes, on January 14, 2005, it managed to send back to Earth information and images of a hitherto unequaled quality. The Surface Science module reveals that underneath a hard, thin crust, the soil has the consistency of sand. Titan's landscapes have similarities with those of Earth. Mists, traces of precipitation, erosion, river systems, dry lakes, coastal landscapes, and island chains. The physical processes that have shaped Titan are very similar to those that have shaped the Earth. However, the materials are more exotic. Since water is replaced by methane, which can exist in liquid or gaseous forms on Titan's surface. When it rains, methane precipitation, mixed with traces of hydrocarbons, deposits substances from the atmosphere on the ground. According to this information, Titan has a uniform atmosphere, made of different gases, methane, nitrogen, and, on the ground, a cryovolcanic activity and abundant liquid methane in the form of rivers and lakes. On its ground, frozen at negative 292 degrees Fahrenheit, according to measurements on the spot, are countless ice pebbles, sometimes as big as cars. The mission also discovered Lake Ontario, a liquid ethane lake that is the first place in the solar system outside of Earth where liquid has been detected on the surface. The landing itself raises some questions. The probe was supposed to emerge from the haze at an altitude of between 30 and 40 miles. In fact, Huygens began to emerge from the clouds only 20 miles above the surface. This could mean a change in the wind direction at that altitude. The sounds recorded when the probe landed suggest that it reached a more or less muddy surface. With an orbital distance of 600,000 miles, it is the second largest moon of Saturn and makes a single orbit every 16 days. Like Europa and Ganymede, Titan is thought to have a subsurface ocean of water mixed with ammonia, which can erupt on the moon's surface and lead to cryovolcanism. The presence of this ocean, as well as the prebiotic environment on Titan, has led some to suggest that life could exist there. Such life could take the form of microbes and extremophiles in the inner ocean, or could take the even more extreme form of methanogenic life forms. As has been suggested, life could exist in Titan's liquid methane lakes, just as organisms on Earth live in water. Such organisms would inhale dihydrogen H2 instead of oxygen gas O2, metabolize it with acetylene instead of glucose, then exhale methane instead of carbon dioxide. Iapetus. With a diameter of 1,000 miles and a mass of 40 times 10 to the 20th pounds, Iapetus is the third largest moon of Saturn, and at a distance of 1,800,000 miles from Saturn, it is the furthest of the large moons and takes 79 days to complete a single orbit. Because of its unusual color and composition, its main hemisphere is dark and black, while its rear hemisphere is much brighter, it is often called the yin and yang of Saturn's moons. The Cassini spacecraft is helping to find an answer to this centuries-old enigma. Its instruments, working in the infrared, discover that Thebe is at the origin of a ring, formed by debris torn from the moon by meteorite impacts. Very tenuous, this ring is not discovered by the astronomers carrying out their observations from the Earth. Iapetus, circulating in the region of this ring, accumulates on the front face, turned in the direction of its displacement, the materials resulting from Thebe, which gives its dark color. Although it is the third largest moon of Saturn, Iapetus orbits much further from Saturn than Titan. Like many of Saturn's moons, especially Tethys, Mimas, and Rhea, Iapetus has a low density, indicating that it is composed mainly of water ice and about 20% rock. But unlike most of Saturn's larger moons, its general shape is neither spherical nor ellipsoidal, but consists of flattened poles and a domed waist. Its broad and unusually high equatorial ridge also contributes to its disproportionate shape. For this reason, Iapetus is the largest known moon not to have reached hydrostatic equilibrium. Thebe. Thebe is the most distant moon of significant size. It is located 8 million miles from Saturn. It circulates on a retrograde orbit of 173 degrees. Of a regular spherical shape, it has a diameter of about 130 miles and is very dark. The only images prior to the Cassini mission were taken by Voyager 2 in 1981. Cassini flew over the moon only once because it is located outside the orbit of the space probe. On June 11, 2004, Cassini passed at 1,280 miles of Thebe and managed to photograph practically all of its surface, thanks to the speed of rotation of the moon. This one presents a very dark surface, covered with craters, some as large as 50 miles in diameter, with walls that can reach 10 miles high. Thebe is probably a protoplanet, with characteristics close to Pluto, which forms in the Kuiper belt at the very beginning of the history of the solar system. It undergoes a process of planetary differentiation at the beginning of its existence. After cooling, its surface is hammered by impacts, giving it its current irregular shape. It is then captured by the planet Saturn. Hyperion. Cassini provided the first detailed observations of Hyperion, the largest of the irregular, non-spherical satellites of the solar system. Voyager 2, which flew over it in 1981 from a great distance, has allowed us to draw a first portrait of this potato-shaped moon. Covered with deep craters and presenting a chaotic rotation axis, probably resulting from the destruction of a celestial body of a larger size. The spectacular photos taken by Cassini show a world reminiscent of a sponge. The very deep craters, which riddled its surface almost without trace of ejecta, are probably related to the very high porosity and low density of the moon. The bombardment of meteorites has not ejected the materials, but has compressed them. The walls of the craters are shiny, betraying the presence of water ice. The bottom of the craters is dark and reddish because the very low temperature of -292 degrees Fahrenheit causes the sublimation of volatile materials and the accumulation of darker materials. The low albedo of Hyperion would be due to the presence of carbon dioxide and other hydrocarbons, including methane escaped from Titan. The Cassini-Huygens mission made it possible to discover, at the end of 2012, about 10 new small moons, all less than 6 miles in diameter, which were added to the 50 or so moons known or discovered in recent years using Earth-based telescopes. Uranus. Uranus is not the largest, nor the most favorable to shelter life, nor the most media-friendly planet of the solar system. However, the icy gas giant has its share of curiosities, and much remains to be discovered about its nature. Uranus is, with Neptune, the only representative of the icy giant planets of our solar system. It is located at about 2 billion miles from our star, in 7th position with respect to the Sun. The atmosphere is mainly made of hydrogen at 83% and helium at 15%. It surrounds a mantle of volatile components: water, ammonia, and methane. In spite of their state between liquid and solid, the latter are called ices, hence the name of icy giant of Uranus. The planet has in its center a core the size of the Earth, made of silicate rocks, iron, and nickel. Icy giants have a mass much lower than Jupiter or Saturn, but still represent the equivalent of 10 to 50 Earth masses. Uranus, for example, is 14.5 times more massive than the Earth. But only 20% of this mass corresponds to hydrogen, while in the case of Saturn or Jupiter, hydrogen represents 90%. An important part of the mass of Uranus is in fact stored in its ices. Voyager 2, launched by the American Space Agency with its twin Voyager 1 to study the planets of the outer solar system, is to date the only probe to have flown over Uranus. It was in 1986, during a little more than 5.5 hours. Voyager 2 passed at 50,000 miles altitude, close to the planet, and brought to light a star without particular distinction in visible light, but with many specificities. Voyager 2 has notably allowed us to collect clues to explain why the planet Uranus is lying on its orbit. Contrary to the other planets, whose rotation axis is perpendicular to the orbit around the Sun, the rotation axis of Uranus is practically included in its revolution plane around our star. The planet rolls on its orbit and presents alternately its north pole and its south pole to the Sun, a unique feature in the solar system. According to a study, this inclination could be explained by an impact 4 billion years ago with a massive celestial object that would measure twice the size of the Earth, a protoplanet. This collision could also explain the very low temperature of the atmosphere of Uranus. The debris of the impacting object would have then formed a shell in the lower atmosphere, preventing the heat from the center to move towards the upper atmosphere. Other theories suggest a progressive tilting of the whole Uranus system due to the presence of a satellite about 100 times less massive than the planet and now disappeared. To this day, the question of the tilt of the rotation axis remains unsolved. Voyager 2 also discovered 10 moons, all less than 100 miles in diameter, in addition to the 5 already known in the late 1970s. It also revealed the presence of a magnetic field similar in intensity to that of the Earth. Finally, the probe showed that the 9 rings of Uranus already discovered at the time were not formed at the same time as the planet, but well after. As said before, the planet has been visited and studied at short distance by only one space probe, Voyager 2 in 1986, which is therefore the source of most of the known information about the planet. The main objective of the Voyager mission being the study of Jupiter and Saturn systems, the flyby of Uranus is only possible because these systems have been perfectly performed before. The probe studied the structure and chemical composition of Uranus's atmosphere, including its unique climate, caused by its 97-degree axial tilt. By examining the 9 rings of Uranus, it discovered 2 others and established their appearance as relatively recent. Voyager 1 could not visit Uranus because the investigation of a moon Saturn, Titan, was considered a priority. This trajectory then took the probe out of the elliptic plane, ending its planetology mission. Since Voyager 2, several missions toward Uranus have been thought about. However, for budgetary reasons, none of them have been realized yet. Neptune. Like Uranus, Neptune is an icy giant. The furthest planet from our star, it is the seat of the most violent storms of the solar system. With the azure blue hue of unknown origin and diamond showers, Neptune conceals incredible wealth. Its internal composition is similar to that of Uranus. Neptune would have a rocky core of iron and silicates itself, surrounded by water, methane, and hydrocarbons in various states ranging from solid to liquid. An atmosphere of hydrogen, helium, and methane would surround the whole planet. Neptune's atmosphere is composed primarily of 84% hydrogen, 12% helium, and 1.5% methane, with some traces of ammonia, ethane, and acetylene. It is the methane that absorbs the light in the wavelengths towards the red and makes Neptune appear blue. But the blue so particular of Neptune approaches azure. The methane alone cannot be responsible for such a tint. With only methane, Neptune would appear blue-green like Uranus. Other chemical elements, still unknown, are therefore responsible for this characteristic color. Voyager 2 is the first and only space probe to have visited Neptune, and the source of most of the current knowledge of the planet. The trajectory through the Neptunian system is finalized once the flyby of Uranus and its moons is completed. As it must be the last passage of Voyager 2 near a planet, there are no constraints on the way to leave the planetary system, and several choices are possible. The scientific team thus opts for a passage at a short distance from the North Pole of Neptune, which will allow us to use the gravitational assistance of the planet to make the probe dive under the ellipse for a close flyby of Triton, the main moon of Neptune, whatever the consequences of the trajectory, in a similar way to what had been done with Voyager 1 with Saturn and its moon Titan. The first observations were made in March 1989, 90 days before the closest passage of Neptune, and nearly 3 years after the flyby of Uranus. They allowed the discovery of Neptune's rings, whose existence had never been proven before. They are composed of very fine particles that do not allow their observation from Earth. A magnetic field is detected and measured, this one being offset from the geological center and inclined like that of Uranus, but of much weaker intensity. During the crossing of the Neptunian system, 6 new moons, including Larissa, are discovered. Due to the distance of Voyager 2, it is difficult to send new instructions for the observation of these new celestial bodies. Only Proteus, 250 miles in diameter, is discovered early enough to program detailed observations. Indeed, the signals of the probe required 246 minutes to reach the Earth, and the mission of Voyager 2 was based on preloaded commands. During the flyby of Neptune, Voyager 2 passed within 3,000 miles of the planet's North Pole. The atmosphere of Neptune was analyzed. Despite the little solar energy received because of its distance, only 3% of what Jupiter receives, an atmospheric dynamic is observed with manifestations like the Great Dark Spot and clouds. Winds moving at more than 1,000 miles an hour were measured. The study of the magnetic field allows us to determine that the duration of a rotation is 16 hours. The flyby also provided the first accurate measurement of Neptune's mass, which was found to be 0.5% less than previously calculated. This new value then refuted the hypothesis that an undiscovered planet X was acting on the orbits of Neptune and Uranus. Voyager 2 passed at a little less than 25,000 miles from Triton and collected very precise data on this moon. The scientific community estimated at the time that the diameter of Triton was between 2,500 and 3,000 miles. The probe allows us to reduce this figure to 2,000 miles. Very few craters are observed, which is explained by the volcanism whose manifestations in the form of traces left by geysers are observed at the poles. A tenuous atmosphere, about 1% that of the Earth, probably resulting from the activity, is detected by Voyager 2. The temperature of the surface of Triton, -391 degrees Fahrenheit, is the coldest ever detected on a celestial body of the solar system. Unlike all the other large moons of the solar system, Triton orbits Neptune in a clockwise direction, as seen from above. Triton could not have been formed at the same time as the planet from the same accretion disk, but must have been captured by Neptune. Triton would actually come from the Kuiper belt. In the depths of Neptune, the pressure can reach 600 gigapascals, and the temperature 12,000 degrees Fahrenheit. Under such conditions, the carbon contained in the planet's hydrocarbons could then be transformed into diamond. In 2017, scientists actually proved the feasibility of this chemical reaction. The small diamonds formed in the intermediate layer of Neptune would then fall towards the nucleus, giving rise to a shower of nanodiamonds. The fate of these Neptunian gems is still poorly known. A solid envelope of diamond around the core, or a sea of hydrocarbons strewn with diamond icebergs, the choice is yours. After crossing the Neptune planetary system, Voyager 2 left the orbit at an angle of -30 degrees. The steerable platform carrying some of the instruments is deactivated, but some of the remaining instruments continue to collect data on the environment. Voyager 2 crosses the limit of the Sun's terminal shock in August 2007 at 84 astronomical units from the Sun and leaves the magnetic solar system, delimited by the heliopause for good in November 2018. The probe is heading towards the constellations of Sagittarius and Peacock. In about 40,000 years, Voyager 2 is scheduled to pass at a distance of 1.7 light-years from the star Ross 248, located in the constellation Andromeda. NASA has long considered a mission to study Uranus and Neptune simultaneously, but for budgetary reasons, only one of the two planets at a time could be explored. Hubble observations in 2017 showed unsuspected activity in Uranus, hence the initial attraction to this icy giant. However, the scientific interest for the Neptunian moon Triton, seat of an active volcanism, took over. It is thus towards Neptune that the next large-scale mission dedicated to the study of an external planet should launch. The probe will have to fly over Jupiter to benefit from its gravitational assistance, which can only occur every 12 years in a very specific alignment of the planets. The next launch window is thus planned for 2028 to 2030, with an arrival around Neptune around 2043. Pluto, ninth planet of the solar system until 2006, the dwarf planet has always been a difficult target for space exploration because of its great distance from the Earth of almost 3 billion miles, but also its strong inclination of its orbit at 17 degrees and its very low mass. But on July 14, 2015, arriving at the closest to Pluto as any other spacecraft, the cards are shuffled with the probe New Horizon. Pluto is a trans-Neptunian object that has the particularity of forming a double system with its moon Charon. Scientists expected to find a world with common characteristics. The first observations go well beyond the expected expectations. Pluto, like Charon, presents young surfaces, practically devoid of craters, with apparent structures both original and diversified. Pluto is still a geologically active planet, with water ice mountains more than 2 miles high. The first pictures of Pluto taken by the spacecraft show a very bright region at one pole and a dark band at the equator. The diameter of Pluto is measured with an improved accuracy and estimated at 1,500 miles. Pluto has a polar cap composed of methane and nitrogen ice. The dark areas have a very different composition from the polar caps, with a much lower presence of methane. Pluto shows a planet with a wide variety of terrain types, showing some of the apparent characteristics of Saturn's satellite Iapetus and Neptune's satellite Triton. The surface is devoid of impact craters and therefore probably young, less than 100 million years old. On Pluto's surface, you'll find high mountains of a height of about 3,300 yards. These cannot be composed of methane ice, carbon monoxide, or nitrogen because these materials are not strong enough to form such high peaks. They're probably made of water ice, which forms the mantle of the dwarf planet. Reliefs of this type have so far only been observed on the icy satellites of gas planets, and result from the tidal forces generated by these giant planets. Here, a different mechanism is at work, but it remains to be determined. Scientists exclude the influence of tidal forces generated by Charon given its size. Two tracks are evoked: the decay of radioactive materials, such as thorium or uranium, present in silicates, which still play a role in the case of the Earth, but whose influence is usually considered negligible after 4 billion years on worlds the size of Pluto. The other explanation assumes the existence of an ocean under the icy mantle, which, by losing its latent heat, would be at the origin of the movements of the surface. The presence of an atmosphere on Pluto has been known since 1988. The New Horizons instruments have confirmed that the atmospheric escape rate from Pluto's atmosphere is particularly high. The solar wind is probably at the origin of the process by dragging ionized particles of the Plutonian atmosphere, unprotected because of the lack of magnetic field, towards the interplanetary space. Scientists estimate, from data collected by New Horizons instruments, that the escape rate is 500 times higher than that of Mars. The atmosphere of Pluto is being reconstituted by the sublimation of materials from the surface of the dwarf planet. This process would have led, since the formation of Pluto, to a reduction of its diameter of 3 miles. Because of Pluto's elliptical orbit, as it moves away from the Sun, its atmosphere cools, then condenses, and is precipitated onto the ground in the form of ice, eventually leading to its total disappearance until the planet approaches our star again. A photo taken at the time of the occultation of the Sun by Pluto has allowed us to highlight the presence of haze up to an altitude of 80 miles. The same photo allows us to distinguish 2 atmospheric layers with distinct characteristics. Charon, like Pluto, shows a young surface with few craters and many formations, suggesting that it is geologically active despite its small size. A 6 to 10 kilometer deep and long canyon is visible near the pole, as well as another 5 kilometer deep canyon. A series of cliffs and depressions run from northeast to southwest for more than 1,000 kilometers, which may have been created by an internal process. Below these formations, a nearly featureless and weakly cratered terrain suggests recent resurfacing. A dark region, nicknamed Mordor, covers the pole and is surrounded by reddish terrain. The dark color could be due to a thin layer of material, as lighter terrain appears where craters are visible. A close-up of a region of the moon near the terminator shows very smooth terrain with sharply drawn impact craters and long cracks. These cracks resemble lunar crevices that originate from the cooling and contraction of very fluid lava that had spread over its surface. An isolated mountain located in a very hollow depression intrigues planetologists because its formation remains unexplained, and this type of formation has never been observed in the solar system. No atmosphere was detected by the probe. Pluto has 5 satellites, but only 2 have been photographed. A first image of Hydra with a few pixels could be taken. With an elongated shape, its surface is mainly made of water ice. An image, also strongly pixelized, of Nix is restored a few days after the flyby. It confirms the length of 40 kilometers and the elongated shape of this small satellite. The Pluto flyby allows us to refine the main characteristics of the small moons of Pluto. One of the most surprising elements discovered by the spacecraft is that, unlike most satellites of the planets in the solar system, Pluto's small moons are not in synchronous rotation with Pluto, i.e., they do not always present the same face to the dwarf planet. In particular, Hydra, the outermost satellite, travels around Pluto in 38 days, while it rotates on itself in 10 hours. Despite these characteristics, scientists believe, given their appearance close to those of Charon and Pluto, that the small moons were formed within the Plutonian system, probably as a result of the merger of small bodies, resulting themselves from the fragmentation of former moons of Pluto. After the flyby of Pluto, New Horizons crosses the Kuiper belt, which extends from 30 to 55 astronomical units from the Sun, and whose study constitutes the second objective of the mission, leaving behind it still a lot of mystery on the dwarf planet. The distant Kuiper belt is a belt of icy asteroids orbiting the solar system. Most of the dwarf planets of the solar system are located in this belt. For example, Pluto and its main moon Charon. The belt starts at 30 astronomical units from the Sun and seems to end at 55 astronomical units. Beyond, we find a less populated region, but we still find dwarf planets, like Eris and Sedna, and smaller objects. Only 2 objects of the Kuiper belt have been explored so far, thanks to the New Horizons probe. The probe has been able to take some pictures of relatively close objects. For example, in November 2015 and April 2016 of Auron, a quasi-satellite of Pluto, which allowed us to gather some physical details, such as its rotation period. At the time, it was 68 million miles from the probe. When the mission was launched in 2006, no trans-Neptunian object within range of New Horizons was known in the Kuiper belt, given the limited amount of propellant the spacecraft would have after crossing Pluto. But mission officials are counting on discoveries in the decade between launch and the trajectory correction that will be needed to steer the space probe to its second target, the Kuiper belt. But after 8 years of research by astronomers, no potential target was discovered by the astronomical community in the Kuiper belt. The deadline for an exploitable discovery was the summer of 2014. To organize a rendezvous, it is necessary to know the orbit of the object that's flown over, which is supposed to carry out 2 observations at 1-year intervals. The first observation must then have taken place on summer 2014 to allow the astronomers to direct the probe toward its second object after the flyby of Pluto in July 2015. The discovery of a trans-Neptunian object within range of the space probe is not easy, because objects of the Kuiper belt are not very numerous, about 1,000 discovered in a huge volume of space, and are very difficult to detect because of their small size and their distance, a few tens of astronomical units between them. Yet significant resources were used to discover a target between 2011 and 2013. An intense observing campaign was conducted using the most powerful ground-based telescopes. 52 new objects belonging to the Kuiper belt were discovered, but none were in range of New Horizons. The closest one required a maneuver that requires more propellant than was still available in the probe. Finally, in October 2014, the New Horizons team announced that it had discovered at least one target that the space probe is certain to fly past, given the fuel reserves it has. 2 other potential targets, close in diameter and at nearly the same distance, continue to be studied. The collection of scientific data on the Kuiper object proceeded in the same way as for the Plutonian system, but the course of the flyby is much more difficult. With limited precision on the object's orbit, the scientists would have to make late corrections on the trajectory of the probe. The Kuiper object was spotted for the first time in images taken by the spacecraft's camera on August 16, 2018, while New Horizons was 100 million miles from its target. New Horizons flew past Arrokoth on July 1, 2019, at a distance of 2,000 miles and a speed of 9 miles a second. At the time of the flyby, the Earth was 4.1 billion miles away. After 4 hours, the first data from the flyby arrived. About 6.25 gigabytes were recorded during this brief passage. Considering the reduced data rate to 1 kilobit a second and the limited amount of energy available, the transmission of this data took about 20 months and lasted until September 2020. According to a first low-resolution photo received the day after the flyby, Arrokoth is made of 2 almost spherical bodies of unequal size, welded together and having the shape of a snowman. It is a particularly well-preserved example of a binary body with contact. The impact must have been made at a low speed of a few miles an hour. These binaries are very common among comets that share the same origins as Arrokoth. The whole body is roughly 20 miles by 9 miles. The 2 elements have been provisionally nicknamed Ultima for the larger and Thule for the smaller. The period of rotation measured shortly before the flyby was about 15 hours. The surface seems devoid of craters of important size. The surface has a reddish color similar to that of the cap of the North Pole of Charon and is probably due to the presence of organic polymer-like materials. The The visible features suggest that this Kuiper belt object was created at the very beginning of the formation of the solar system, and that it has retained its original characteristics. New Horizons' mission could continue until 2025, by which time the spacecraft will have reached the 50 to 60 astronomical unit distance where the outer edge of the Kuiper belt is located. Beyond that lies only scattered objects whose density makes a flyby unlikely. The mission project team hopes to find a third target for the spacecraft in the Kuiper belt. This discovery could be difficult considering the particularly significant means that had to be mobilized to find Arrokoth. However, the probe should itself detect the object it could visit. It should make the analysis of the photos it'll take and could detect an object with a luminosity too weak to be seen from the terrestrial telescopes. This new target must be discovered in the next few years before the spacecraft leaves the dense Kuiper belt region. In January 2018, the New Horizons and Voyager teams met to lay the groundwork for a possible collaboration to observe the heliosphere. The instruments and positions of the three spacecraft, Voyager 1 and 2 as well as New Horizon, may complement each other at least until 2025 and possibly until 2027, when the amount of energy left in the Voyager probes will no longer be sufficient to keep them operating. By 2032, when New Horizons will be located at about 82 astronomical units, the remaining power in the spacecraft will be 150 watts, the minimum required to keep it operational. While it is probably possible to push these theoretical limits, the probe will definitely not be operational by the time it reaches the distance of 120 astronomical units. But then, what is beyond the Kuiper belt? First of all, it's important to know that the further an object is from the Sun, the more difficult it is to detect because it is less illuminated, and difficult to observe because of the distance. At about 55 astronomical units from the Sun, we notice that the number of objects decreases sharply. We call this area the Kuiper Cliff. This area could mark the outer limit of the belt. However, beyond, space is not empty. Other objects exist in this distant region called the sparse disk, including dwarf planets like Eris, which is about the same size as Pluto, and Sedna. Eris is currently located about 95 astronomical units from the Sun, but its orbit will bring it back into the Kuiper belt in a few hundred years before it leaves again. Sedna belongs to another category of objects, the detached objects. Currently located at 85 astronomical units from the Sun, Sedna will pass to 76 astronomical units around 2080, then will leave to a distance of 950 astronomical units from the Sun, 10 times further than Eris. Smaller objects are known to go even farther, up to 3,000 astronomical units. Beyond that, around 20,000 astronomical units, is the Oort cloud, made up of billions of comets. It has never been observed because it is too far away, but its existence is almost certain, because some comets come from very far away. We do not know where it ends, but the Oort cloud could go up to 100,000 astronomical units. That is to say, more than 1 light year, which gives you some idea of the size of the universe.